All right. So we are talking about now pressure and ideal gases. So we'll relate all the two, see what is actually found in gases. Okay, so gases in short. So let us get started now. So gases actually there's the gases are just bulk. Okay. Mm, clinic. Okay, maybe. What was the uncle? Okay, so what you are trying to say is now these gases will look at the characteristics, the behaviors which are just characteristics. Then we'll talk about okay. So so gases, okay. So what do we mean when we say gases? So gases actually can exist. I mean, just the same matter we learned from the date can exist in gas, liquid, and solid. So today we'll talk about the same gases now in details. So gases have the lowest density. Yes, you can't even feel them, but they are there. Take gases as air. So gases have the lowest density of the three that we have here. So most density is this one, followed by this, then followed by that. So, and what do they do? Once these gases, they can be compressed in a balloon. You can compress a balloon, right? And they will take the shape of their vessels where they are pressed in. They will take the shape of the container where they are. So you can put a gas in a gas cylinder. It's there, but you won't see it. You take the shape of the container. That's the shape. So if you are to give the characteristic as part of shape, you say the shape of their vessels. So elements that exist as gases at room temperature and pressure are clustered on the light of a periodic table. So they are placed on the light of the periodic table, like in oxygen, we have the sulfur guys, carbon guys, and so on. When chlorine guys, you have them there. So they occur as either monoatomic gases, which are just, let's say, noble gases like helium gas. It doesn't occur as two like that. So mono, it means just one gas. Most of them, but they occur as diatomic, like N2O, I mean N2O2, just like that. Okay, so we have gases. So these gases can expand spontaneously to fill the container in which they are actually held in. So by doing that, they exert a pressure on the wall of that vessels or a container where they are pressed in. So we'll look at now the pressure of gases. So we'll be able to see how we can calculate the pressure that they are giving. So to the wall. So they will give a pressure, let's say in a balloon. So we'll look at now what is this pressure that they are giving. First of all, First of all, pressure is defined as the force exerted per unit area. It can be measured using barometer or manometer. So I've demonstrated the two instruments that can be used to measure pressure. So let me say something. So pressure is defined as the force per unit area. Okay. So you can say pressure is the force per unit area. So the force divided by the area. Okay, the force that you apply to the area is the pressure that you have. So it can be measured using the instrument barometer or manometer. Okay, so the barometer looks like this. So the barometer looks like this. Okay, so the barometer looks like this. So the barometer looks like this. We have the barometer. So this one measures the pressure of the atmosphere at sea level. Okay. So at sea level now outside the environment to be able to measure the gas, the pressure it can give outside. But for this one, manometer measure the pressure of the gas in a container. So the pressure that is giving to the wall, that pressure that a gas can give to the wall against the wall, let's say in this one, is what we call the manometer to be used. I mean, when measuring it, when measuring that such type of pressure. But the pressure again above the sea level, um, at sea level, we use what we call a barometer. So barometer used in geography, but here you are finding manometer because we're interested in where they are pressed in, and that's the vessels where. So it has these units, and I mean the diagram. This is how they looks. So, but what is important is actually to master this one. To say 1 atm is equals to 760 millimeter of mercury. Okay. So pressure. All right. So let me just, I can't move my case. I don't know why it's like this. So pressure, like we said, pressure is now, um, pressure is the force per unit area of a surface or a wall. The SI unit for pressure is actually Pascal. This Pascal is equal to the same Newton per meter because we'll be actually calculating the force over area. Area which is drum. So pressure pressure is now, I mean force we have newtons, then the meter is now from area. Okay, so that's why we have these units. So these units, they are equal to Pascal. Okay, so what you are going to do is, um um what you are going to do is, we'll now look at the conversion of units. Okay, why my cursor is not moving? Okay, so we are talking about now pressure SI unit. So what we need to know is that we'll be using this ATM, or whatever will be given, but ATM is the one we'll be using in our equations. So we have 660, I mean 760, 760. We have 760 is equal to 1 ATM. Again, the same 760 is equal to 1 ATM torrs. So we have 1 ATM 1 ATM atmospheric pressure is equal to 760 millimeter of mercury. Again, the same 1 atm is called 760 torr or torriques. Then we have again the same 1 atm is equals to Pascal. Remember, Pascal we said is equals to Newton per meter. That's why I've just replaced the same value, and these ones, they are not that important, so you can leave them at your stage. You don't use them unless when you specialize in chemistry. So that is it. So master 760 millimeter of mercury, again 760 toric, then 10 13 25 Pascal. This one is just same as this one. So 10 13 25, 10 13 25, 10 13 25, just like that. You can master it like that. So I'll be using these conversions, so pay attention to it. So we have gas laws now. The first gas law that we'll start with is the pressure volume. So the relation is the pressure volume of actually will be inverse to each other, because let's say you have this volume is big, right? The radius even big. So the pressure won't be that much, but as you reduce the volume, the pressure will increase. You have seen the pressure is about how these gases will be exerting a force on a wall. So you compress a gas, you actually increase the pressure in the vessel, in a balloon. So Boyle's law state that the volume, okay, of a fixed mass or quantity of a gas at constant temperature, you have to maintain temperature, because if you don't maintain temperature in a balloon like that, temperature also increase the pressure. You get? So you maintain temperature, which actually reduce the kinetic energy, and level actually the kinetic energy. So temperature will keep it constant, but will reduce now the volume, and see how pressure will increase. Okay, so it is inversely proportional to each other. You increase this one, you reduce this one. You reduce this one, you increase this one. So that's how they actually come to this one. So we are saying now volume is equals to 1 over P. They are inversely proportions. That means that they must be K constant there. So you multiply throughout. So that will be Vp is equals to K. So since K is constant, it can give again Vp 2 2. These can be 1. So that's the formula. That's how it came about, this one. Okay, So that is it. Okay. So the diagram representation of actually the, you see it to be going inversely like that. As this one increase, this one reduces. You have seen? So that's how the inverse proportion will be seen. So this is the graphical representation of the law that we have just mentioned. So let us tackle some examples. So see, we know now that this relation is PV1 is equals to PV2, P2V, like that. Okay, this is the relationship that we obtained. We have seen that how it came about. So we have now, they have given us 20. You try these examples, by the way. I'll just give you the way to do out. Get your calculator and try what I'm trying to say. So we have 20.5 liters of nitrogen. By the way, volume always should be in liters or decimeter cubed. So this decimeter cubed is same as liter. So no pressure, no issues here. So nitrogen at 25 degrees. So this was the maintained constant temperature. And the pressure which was given is, the initial pressure is 742 compressed to um, 9.8 atm. So we are talking about pressure now. We need to have pressure 1 and pressure 2. We are looking at the volume 2. Okay. So the volume 2. Now here, the volume 1 we have is there. But what we don't have is the pressure in atm. You have seen? So it's just a matter of changing atm. So we know that 1 atm is equal to 760 millimeter of mercury, right? So we have now that one, which is 742. So we find the atm next. So once you find the atm x, then is the one you put in the formula there as the pressure 2. As the pressure 2, then the pressure 1 we have is 9.8. So you'll be able to find there. You have seen? So try it, please try it. I've given you the hint. It's just a matter of converting this pressure. You convert this pressure, given the conversion that we looked at above, convert it to atm, then you press in the formula P1, V1 is equals to P2, V2. So we have pressure 1. Pressure 1 is this one after you convert. Then pressure 2 is actually which was compressed. Then volume 1 we have is that one. Then you find V2. You'll be able to find as 2 liters. So just check. So again, this one, let me help you to analyze. We have 30.6 millimeters of carbon dioxide at 760, again 740 millimeter is expanded at a constant temperature. So a constant temperature is not known, but is expanded to that temperature to a volume of what? 7. So we have this volume to this one. You've seen it has increased. So what is the final pressure in kilopascal? So we'll calculate the pressure in pascal. Okay. Remember, so here it's somehow advanced. What we are going to do is first to take this one into ATM. Okay. From there, after taking it into ATM, then take it into pascals. Okay, because that ATM value you get, you relate it to pascal value from the conversion that you looked at on the previous page. Okay. Hope that is not confusing. You change this one to ATM, then the kilopascal, this one will come later. This is just 1000. Okay. You divide by 1000 to get a kilo. So you convert that, then use the same gas law that we are from talking about. Then the volume, everything is okay, it's just this one, and find the pressure 2. Once you find that pressure 2, then you'll be able to find it. You divide by 1000, then you get that kilo. You attach a K there. You know how to find the kilo something. Then consider reaction. Consider 1.53 liters sample of sulfur dioxide at a pressure of 55.6 times that pascal. So we have pascal. If the pressure is changed to this one pascal at a constant temperature, what will be the new volume? So even here, this one is just direct. You have seen this is direct. Just you apply PV11 is equals to P2V2 like that. You apply, you'll be able to find the final volume. Everything, the P1 is there, the P2 is there. Everything now you just find this. So you punch, you'll be able to find this one. Okay. That is it about this one. Very simple. So I was just giving you, try with your calculator. That's how we learn. Okay. I've explained out what to do. Then we have also Charles law. So this Charles law actually also relate temperature to volume at a constant pressure. So here we are maintaining a pressure. Okay. So we maintain pressure and see how this volume is changing with temperature. Okay. So when you have these gases, right? Then you increase the temperature there. What will happen to the volume? Because the kinetic energy there of the gases will increase, so they will exert more pressure, so the volume also increase. Okay, so the volume increase as well. So that's what will be happening. So it's direct proportion. So this is why we are saying the volume of a fixed mass is direct proportion to the Kelvin temperature. Okay, at a constant pressure. So the pressure is constant, but once we increase the temperature kinetic energy there, the volume, these guys, they will exert a pressure also on the wall, and thereby exerting also some volume change. So the volume also go up, the temperature will also go up. So that is it. So by this we can come up with the equation. What we are trying to say is the equation that to come up with is, we have, as the volume increase, the temperature also increase. So thereby there must be also a K. So this means that volume over temperature is equals to K. So this means that we can have volume 1, temperature 1 is equals to, so this can be also is constant, so it can also give other conditions there, 2, then temperature 2. So this can be also volume 2 over temperature 2. Okay, that is it. So that's how it's actually coming to this equation. So this is how we are coming to this equation. Then that means all this is direct, so it will be direct like that. As the other one increases, even the other one increases as well. Okay, so I also explain again these examples. What will be the final volume B if this one of a gas is a gas at 22 degrees is heated to 90? So we are increasing the temperature. Have you seen? If the pressure is held constant, so this is the volume. So we just apply the same formula. Very simple, guys. So we apply the same V1 over T1 is equals to V2 over T2. So we have here the volume 1 is that we are looking for this one, this volume. Then we have temperature 1, then we have temperature. So since you can take this temperature in Kelvin, but it still give you the same. It's matching, but you can take in Kelvin for the sake of sake, but they are of the same size, so they relate to each other. So you can just use even the way they are there, like that. So at what temperature would be this volume gas at this temperature have volume of this one? This is the final volume at so this is still the same. Very simple. Like we are applying the same formula. V1 over temperature 1 is equals to V2 over temperature 2. So temperature 1 we have is this one. Then we are looking at the temperature, right? We'll report this temperature in Kelvin. That's the standard. So if you want, you can convert this one into Kelvin, or you leave it and convert later the answer in Kelvin. So it's just a matter of substituting. V1 we have there, V2 we have there, temperature 1 we have there. So we are looking for temperature 2, and you'll be able to find this from that equation, this one. So it's a sample of the gas at 15 degrees Celsius and 1 atm has a volume of this one. What new volume will gas occupy at 30 degrees? This one is constant. This is the what is being kept constant. So we have the temperature there and the temperature there. So we have the V1, but you don't have the V2. So you use the same formula and you do the same. Try. Pause the video and you calculate actually. Okay. So that is it about this one. So we do Avogadro's constant. Avogadro's constant or law, just the law by the way. This one relates the volume to number of moles. Okay. As you increase the number of moles, you increase. So equal volume of gases at the same temperature and pressure contain the same number of moles. So the same volumes equal to the number of moles or particles. Okay, so that's why he's saying now volume will be giving the same number of moles. Okay, so volume is equals to K. There must be K in each variation, so we divide throughout by the number of moles, so we'll get K. So V over N is equals to K. Then we relate, this is constant, so we'll have V2 over N2 if this first condition. So that's how we came up with this equation here. So mass, that to say equal volume of gases at temperature and pressure. So what is being maintained is um, so what is being maintained is pressure and temperature and pressure. Okay. So the combined gas, now you combine. Remember, the first one was giving this one. Okay. This was the first row for Boyle's law. Then for Charles' law, we could see temperature sitting down there. Okay. So that's how we combined these. So you can also again combine the moles because the moles we are cutting. So that is if you are given a lot of them combined. Okay. So it says for combined one, for fixed mass of a gas, volume is directly proportional to the Kelvin temperature, inversely proportional to the pressure. You just explain how we have combined the two gases, which is Boyle's and the. Okay, so that a fixed mass of a gas has a volume of this one, 76 centimeter cubed at 25 degrees, 37 degrees Celsius, and the pressure. What volume would be occupied by the gas at STP? Okay. So now here, what we have here, we have the pressure one, which is that one, kilopascal. We'll take it into pascals just. So that is the initial. We can take it into ATM, we know that. Then the volume one which they have given is that one, 76. Then the temperature one is now 37. So 37, you take it into Kelvin, is there. Then the pressure that they have given us now is 1 ATM. Okay. So which is in 2 Pascal. So 1 ATM. Okay. Wait. So this is the STP, which is the standard. This is the standard. So we use this pressure as well. So then the T2. The T2, do we have the T2? We don't have. So the T2 at STP is actually this one, 0 degrees. Okay, the temperature at STP is 73, something like that. Okay, 273, I mean. So these are standard. You look at this. This is what actually tells you everything to get the pressure and the volume. Then you replace in this combined gas law. So you'll be able to find your final pressure like that. So try this and see what is being talked about. So what is tricky is this one, this condition, which will give you the two final pressure and also the temperature that is at STP. So it's always at RTP is 25, but at STP is 0 degrees, which is just 273 like that. Okay, the volume find, then you'll be able to find from what we'll be manipulating there. All right. So otherwise, that is it about this one. Thank you very much.